Hey, Discrete Math students. Welcome to this going deeper video on the division algorithm. So we've met the division algorithm in class, and we've noted how it is really kind of deep and powerful theorem that allows us to do so much. But you might wonder, well, how do we know that the division algorithm is true? Okay, I've got it here on the screen for you just as a reminder for every integer b and every positive integer a. There exist unique integers q and r such that both b equals aq plus r and 0 is less than or equal to r is less than a. It's saying a lot. Now you might be expecting, well, we're going to give a proof of the division algorithm. That certainly can be done, potentially even in this class, but it's going to take some advanced proof methods and stuff like that to be able to give a proof of the division algorithm. What we're going to do is give a different kind of justification. So there are different kinds of justifications for different circumstances. A lot of what kind of justification is appropriate is going to depend on your audience. You want to make sure whatever kind of rationale you give for something, it's convincing to the audience at hand. So you can see if you find this particular justification convincing, I hope you will. It may not be as convincing to an audience of professional mathematicians, let's say, but we'll leave that for them to deal with. Okay, so let's go ahead and see why we might want to believe that the division algorithm is true. Let's see if we can get to the next page here. Okay. So this goes back to the origins of the division algorithm. It really at one time was an algorithm, and let's see what that actual algorithm is that's behind the theorem statement that we typically see. Okay, so for this illustration, we're going to start with two integers, a and b, of course, but we are going to suppose that everything's positive here, and that b is greater than or equal to a, and a is greater than 1. The case where a is greater than b, we kind of covered that in class already. We saw it's not a very interesting case. Okay, so everything's positive. We could adjust for negatives if we wanted to, but let's just do this illustration. All right, so let's suppose that b is somewhere like maybe over here. Okay, so what we do, the first step of the algorithm is to subtract a from b. So you can see how big a is by this interval over on the left. And so we'll try to make a similar, I guess I'm going to have to do this right-handed, aren't I? I'm left-handed by nature. Okay, so b minus a is going to be right about there. So there's b minus a. Okay, and so notice we're getting closer to where a is, but we're certainly not there yet. So what we want to check now is our new number b minus a less than a, and if it's not yet, if b minus a is greater than or equal to a, then we subtract a again. So let's go ahead and do that. Right about there, and now we're at b minus 2a. And so what we do is we just keep going with this, as tends to happen with algorithms. You do the step over and over again, you iterate it, and there's got to be a way to know when to stop, right? So you keep on going, and we can think of, again, kind of iterating this, moving over by a's, there's b minus 3a, and so forth. And at some point, whoops, I don't know why that happened. Let's see, are we going to be there yet? Probably not quite. At some point, we get to be less than a. Okay, let's say that is b minus qa, or aq. Maybe qa would be more in keeping with what we've been doing so far with the b minus 2a and so forth. Okay, so we know that is going to happen eventually, right? Because b is initially greater than a. So if we keep subtracting and subtracting and subtracting something positive from b over and over again, it's going to get smaller and smaller. Eventually, it will be less than a. So, that's not probably quite proof level, but hopefully it is believable and makes sense. Okay, so b minus QA or B minus AQ, it turns out that that is going to be our remainder. And Q is the quotient. Q is the number of times we had to subtract. So here's a way that I like to envision what's going on here. Okay, imagine that we've got a bunny here, and the bunny is going to start at B. So here's our bunny. And this particular bunny, it always hops with hops of length A. Okay, so it's going to start hopping towards 0. Takes a hop of length A, another hop of length A, and so forth. All these hops are length A. And what the bunny wants to do is get into the target range, and we'll say that target range is 0 to A. I made that go a little too far. Let's see if I can do it better. So 0 to A, that is our target range. And the target range actually does not include A, but it does include 0. So it's a half-closed, half-open interval like that. Okay, the bunny wants to get into the target range. So the bunny hops, 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 and into the target range the bunny goes. Okay, so there's a couple of things that the division algorithm claims that we want to make sure are, that really happen here. One is that there must be Q and an R that satisfy these conditions. So that says that there has to be some number of hops that the bunny can do to land in the target range. Okay, and is that true? Well, let's see. Again, we've mentioned that eventually that bunny is going to have to hop below A. But could the bunny jump all the way over the target range? Well, no, okay, because if the bunny is not in the target range yet, it is at a location bigger than A. The hops are all length A, and the target range is length A, so there is no way that the bunny can hop over the target range. It's got to land in that target range. And that where it lands, that will be the remainder, and the number of hops it took to get there is the quotient. So the quotient and the remainder must exist. But that's only half the battle, right? Only half of what we need here. We also need that there's only one Q and A that are going to work. So for that, we need to know that there are not two numbers of hops such that the bunny is in the target range. Okay, we already said, yeah, eventually the bunny is going to end up in the target range, right? But could the bunny hop again and still be in the target range? That's the other pressing question here. Well, remember, the bunny's hops are length A. Okay, it's already at a location that is less than A. So if it hops another A to the left, it is going to be now at a negative number, and that is not going to be in the target range anymore. Okay, so there cannot be two numbers of hops that work here. And that, of course, implies that the location that the bunny lands in the target range must be unique as well. As the bunny has its one hop where it lands, its one number of hops where it lands in the target range, its location, its landing spot in that target range will also be unique. Okay, so there you go. The numbers Q and R have to be, not only exist, they also have to be unique. So hopefully that seems like a very convincing or relatively convincing justification for the division algorithm, especially for younger students. I think that this would be a very convincing way to explain it. It's not a so-called rigorous proof, right? It would not pass the mathematical tests or whatever as convincing as it is, because for that, of course, we need all the official language and logical structure and so forth. And we could do that eventually. We'll see if we get around to it. It would require accumulating some sophisticated techniques and stuff like that, and it would look very fancy and so forth. But at the end of the day, what we were doing with the hopping bunny here, that is essentially what would involve, okay, what it would be involved anyway. It effectively uses the same idea, just made more technical sounding. Okay, it'd be in a more elaborate costume, not a bunny costume. Okay, so one thing about this actual algorithm that underlies what we call the division algorithm, you can see that it would get kind of tedious and laborious and lengthy. If B is a lot larger than A, you'd be doing an awful lot of hops before you got to that target zone if you subtract your A just kind of one subtraction at a time. So in practice, what we do is we employ a shortcut. Okay, this is what we could call a turbo hop. Okay, remember this this calculator algorithm? We had mentioned that in class, or will shortly, depending on when you're viewing this video. That process of dividing B by A using real number division on the calculator and then rounding down, what that is doing is it's telling you exactly how many hops you would need to take to get into that target zone. So if we go here and we say, all right, we're going to figure out how many hops it would be, and then we're just going to do all the hopping all the way into the target zone all at once. That's our turbo hop. And that's what the calculator algorithm allows us to do by figuring out exactly what that number of hops would be. And then in step 3, if we get to it here, multiplying Q by A, that tells us the total distance of that turbo hop. And then, of course, we can do the subtraction all at once and figure out where in the target range the bunny landed. Okay, so that is how the calculator algorithm fits in with this. Back in the old days, in theory, anyway, they did just the one hop at a time, and of course they didn't have calculators either, but they probably could have come up with something similar. Anyway, let's not go down that rabbit hole, and we'll leave it at that as far as justifying the division algorithm for now. To be continued. We'll see.